Wireless Internet Service Provider, Wisp. Think of a wireless internet service provider, or WISP, as a massive, high-powered Wi-Fi router for an entire geographic region. If you are driving a rural delivery route outside of NYC, where the physical cable and fiber lines simply stop, you will often see small, specialized antennas mounted on the roofs of isolated homes. This is the hardware of a WISP. It provides a critical bridge for communities that are too spread out for expensive underground cables, but require connection speeds and response times that traditional satellite simply cannot provide. For your CompTIA A+ exam, you must understand the architecture of this point-to-multipoint system, the absolute necessity of line of sight, and how it contrasts with the other technologies we have explored. The architecture, beaming the signal. A WISP operates by broadcasting high-frequency radio waves, often in the 5 GHz or 900 MHz unlicensed bands, across long distances. The architecture starts at a base station. The provider will lease space on top of a water tower, a grain silo, or a high mountain peak. They run a heavy, high-speed fiber optic connection up to that tower. From there, they install sector antennas that broadcast the internet signal out over the surrounding valley. At the destination, the customer receives a piece of CPE, or customer premises equipment. This is usually a small, highly directional parabolic dish or a flat panel antenna mounted on their roof, unlike a smartphone that grabs a signal from any direction. This dish is carefully aimed by a technician to point exactly at the provider's tower on the mountain. A cable then runs from that roof antenna down into the house, plugging into a standard router to provide Wi-Fi for the home. The crucial limitation, line of sight LOS. The defining physical characteristic and the biggest weakness of a WISP connection is the requirement for line of sight, or LOS. Because these networks use high-frequency radio waves to push large amounts of data, the signal is extremely fragile when it hits physical objects. For a WISP connection to be stable, the dish on the roof must have an unobstructed visual path to the tower. If a hill sits between the house and the tower, the connection will fail. Even more common, if a customer has a perfect connection in the winter, but a tree in their yard grows thick leaves in the spring, those leaves can block the radio waves and completely kill the internet. As a technician, troubleshooting a WISP often involves physically moving the antenna higher up on a pole to look over the surrounding trees. Contrast and comparison for the A+ exam. To master this technology, you must be able to contrast a WISP against the other rural and fixed-line options. WISP versus satellite. This is the most common rural debate. A traditional GEO satellite connection has massive latency, over 600 milliseconds, because the data travels to space. A WISP tower is usually only 5 to 10 miles away. This means WISP latency is incredibly low, often around 30 milliseconds. You can easily play competitive video games, run remote home lab sessions, or make VoIP calls on a WISP, which is nearly impossible on old satellite. However, satellite wins on pure coverage. If you are deep in a valley with no line of sight to a local tower, satellite is your only option. WISP versus cellular, 4G/5G. Cellular networks are designed for mobility and use omnidirectional antennas so your phone works while moving. A WISP is a fixed wireless connection. The directional antenna is bolted to a roof and cannot move. However, because a WISP uses a focused, directional beam, it can often pull a much faster and more stable connection over a longer distance than a standard mobile hotspot. WISP versus cable and fiber. Cable and fiber will always offer higher maximum bandwidth and immunity to weather and trees. But burying 10 miles of fiber optic glass through rocky, upstate terrain might cost hundreds of thousands of dollars just to reach 10 houses. A WISP can cover those same 10 houses for a fraction of the cost simply by putting an antenna on a hill. By mastering the directional nature of the hardware and the strict rules of line of sight, you will understand how technicians deliver high-speed data to the edges of the map, where the physical wires end.